Hey everybody, in this video I want to go over the setup and the calibration of your Arduino Shield after you get it built. First step, of course, is to go through and double check all your components, make sure they're in properly, polarity's correct on your items, check the underside of your board for solder bridges. If there's any questions at all, anything looks doubtful, test it with your ohm meter. Make sure you don't have any bridges. And hook up your lead wires. And you'll see on mine, I have put labels on the top of my pot just to make it easier for me to see. The first pot I have here is the attenuation pot. This just attenuates the signal coming back out of that capacitor that you're measuring. This is R5. The frequency adjustment, that's R6. And then the load potentiometer, the span, or whatever you want to call it, that's R9. So just label those. It makes it a little bit easier in the setup to follow along. The first thing after you've checked your board to make sure everything is in tip-top shape is we'll want to go ahead and set it up on the Arduino. Okay, we'll set it up there on top of that. The Arduino's not plugged in yet, no power to it. And before I adjust this, I just want to show you that your values on these, the setup is going to drift, but once you get it set and you get it spanned out, the calibration function inside the Arduino code is going to take care of any of that drift that we see. Because what we're basically doing is we're spanning the attenuation from your cables to the output to the Arduino. So if there is a shift in temperature, it should be linear across both of our pots. So if it shifts high or shifts low, it really doesn't matter because the span is going to remain relatively the same. Inside of the code, I've documented exactly what we're looking for on these values. The first thing we need to do is get your excuse me, get your multimeter and set it in DC voltage. If you have a millivolt setting, that's great. Go ahead and set it up in your millivolt setting, and then you want to put your signal on the A5 pin analog input of your Arduino, and then go ahead and pin out the ground. Okay, there should be no voltage reading. Then if we plug in our Arduino, it's power up there, and we shouldn't see any voltage across these two terminals until we have a device under test between our test leads. So to short this out, you're going to notice we have a millivolt reading of 728. When I initially set this board up, I had it dialed in at 700 millivolts, and it just drifted from temperature. And likewise, you're going to need a 10 ohm resistor, and I'm not going to get into precision. I tested this resistor, just a regular resistor I pulled out of my resistor trays, and it's a 1% resistor, and I tested it across a couple different multimeters, and it's relatively close. It's close enough for this project. Like I said before, I'm not a calibration shop, so if we test this, the way I had it spanned was the voltage across a 10 ohm resistor should be 295 millivolts, and it's drifted up high too. It's at 313. But the main thing is that the Arduino, if we go ahead and plug our display in, even though those initial values have shifted, drifted up and or down, it doesn't matter. They're temperature dependent is what they are. You plug the shield into it and reset the device. If I hit the calibration, well, first let me short the probes and show you that it's out. It's reading negative 0.1 ohms. I hit the calibration button. That zeroes a meter out. Now if I connect it back to my 10 ohm probe, or my 10 ohm resistor, it's going to read 9.91, 9.95 flashing, which is close enough. If I get down here on my 0.2 resistor, it's bouncing 0.22, 0.20. So even though my initial setup values have drifted, it is still, the calibration function in the code will keep it calibrated. You don't need to go back and reset these values every time, and I really don't know how far the values have to shift before it throws it out of calibration. I haven't ran into that yet, and I've had this up and running for several months now. So back to the setup. Let me unplug this. When you first build your board and you get it set up, you have your 3 precision pots, and you really do need to use those 20-turn precision pots. And what you need to do is go through here and center all of them. So I'll just go through and turn these all in either direction. It doesn't really matter, just to make sure they're all the way to the wipers, all the way to one end. And then I'll back it out 10 turns. 1, 2, 3. Okay, that should put that pot near the center, the wiper near the center of the pot. And we'll do the same thing with the frequency. Okay, and then we'll not being very cooperative. We'll back it out 10 turns. So there's 1, 2. Okay, there's 10 on that one. And then the attenuation pot, we'll center it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so now we have our pot centered out. The first thing we need to do is check the frequency, or set the frequency of that comparator oscillator on the first stage of that dual op amp. On your multimeter, you can use a multimeter, you can use your frequency counter, you can use an oscilloscope. It really doesn't make any difference. Everybody pretty much has a multimeter that has a frequency scale on it. The op amp is outputting a 5 volt peak to peak square wave, so all the multimeters should be able to measure this output easily at 5 volts. So we'll put that on the frequency range measurement. We'll go ahead and we'll ground the one lead. And let me get a little micro clip. And I can't find one. Okay, we'll just go ahead and I'll just use my my probe. It's not a deal. What we need to probe is pin 1 of the op amp. That's the output of the first stage of the oscillator comparator. So let me see if I can do this and show you guys what's going on. Oh, we need to power up our Arduino, obviously. And I'm just gonna probe pin 1 and want to set it for 100 kilohertz. Okay, right now you can see right here we're running at 35 kilohertz. Hope you can see that okay. And I'm just going to turn the pot on this. Turn that out until we get about 100 kilohertz. Or whatever frequency you want to run yours at. It really doesn't make any difference. That 100 kilohertz is a suggested, that's where all your capacitors are spec'd at, is 100 kilohertz. Okay. Come on. Okay, so there we're at 100.6. There's 100.1 kilohertz. Okay, great. Now we have the frequency of that oscillator set. Our entire circuit, the measurement is we're going to be measuring our capacitors at 100 kilohertz. Okay, so we can go ahead and switch back to our millivolt range, DC millivolt if you have it. Okay, go ahead and put our probe back in pin 5. Okay, and the first value we want to set is we want to go ahead and set the output of the op amp. So what we're going to do is we're going to short our leads out, and we're reading 815 millivolts. We want to turn this load pot until we get that dialed down to around 700 millivolts. That's the wrong way. Okay, so there's 702. That's plenty close enough for right now. And then get your 10 ohm resistor. Go find you a 10 ohm resistor. Measure it across a couple multimeters if you can. Go buy you a 0.05% 10 ohm resistor. It doesn't matter. Whatever you think that you need to be as precise as. Here's my 10 ohm resistor that I'm using for the calibration. And what we need to do now is on the attenuation pot, the attenuation of our leads, we need to turn the attenuation down until we have a reading of 295 millivolts. Okay, there's 295.7. Now we'll go back and we'll short our leads out again. And you can see that reading has dropped because the attenuation changed on our probes. So what we need to do is just go back and forth on these pots until we get it spanned out to read 700 at the top and 295 at the bottom. And it doesn't usually take very long to do it. Okay, now we're going to go back to 10 ohms. There's our 295. I'm going to go back to short. Again, on the short, when the leads are shorted, we want to be adjusting the load potentiometer. That is R9. Okay. And it doesn't have to be precise, just within a couple millivolts is plenty close enough. We're going to go back to our 10 ohm. resistor, dial it back down to 295. This is why you need those 20 turn precision pots on your board. I don't know if you could do it with just a regular 1-turn pot. Okay, we're shorting our leads out again. We're getting closer each time. Back to the 10 ohm. Back to short. Back to 10 ohms. And we're there. Just a little bit off. Let me go ahead and tweak this. Go back to short. 697. Ten ohms. 296. There's 295 and 699. Just tweak that up one little tidbit, or 700. So we got 7 and 295, 296. Anyway, that's plenty close enough for our span, as I showed you. So we unhook it. We're done with our multimeter now. Go ahead and pull the pins out, and now we can go ahead and connect our LCD shield and reset it. Sorry about that. Forgot to unplug the phone when I was making this video. But anyway, back to the board. We have the shield hooked back up now. Reset the shield, and it's going to read with our test probes open. It's going to show us an open loop. When we short together, we're out of calibration. It's showing us about 0.5 ohms, so we'll hit our calibration button, and it'll take us back and zero it out. Now if we test our 10 ohm resistor, we're reading 9.91 on our 4.7 ohm resistor. We're at 4.67. Our 2.2 ohm resistor, we're at 2.1314. Our 1 ohm resistor is reading 0.9897. Our 0.5 reading 50. Our 0.2 ohm resistor is reading spot on 0.18, 0.2. It may need calibrated again. We're just a couple ticks off on the bottom there, but it's just flashing back and forth between 0 and -2. So let's recalibrate that again. And try it. 0.2. Because if you use the LCD shield on your meter, it does pull a considerable amount of current through the regulator on your Arduino board. So that regulator will put out a little bit of heat, and it'll eventually be absorbed by your board. So your calibration will fluctuate a little bit during the initial warm-up stage of it. Not a lot, like I said. It looks like it's like 20 milliohms. So it's not a whole lot, and I don't think anybody's going to be using this using it for resolution that great. So we're back to reading 0.50, 0.2, So I guess what I'm trying to say, I guess, is just you may just want to let it sit there for a minute before you use it. Let's let it warm up. If you really want some super accuracy, let the temperature acclimate on your shield. This is 4.7, and back to our 10. And again, we have the button on the underneath the shield here that displays our calibration factors. The lead shorted, we should be at 700 millivolts, just as we set up in our calibration, and the ADC is around 680, 681. And that's really all there is to setting this little the shield up and calibrating it. And like it said at the beginning of the video, that I hadn't I set it up initially, and I'd been using it for a couple months and testing it, and I really hadn't had any problems with it until this is the first time that I'd recaled it since I had initially set it up, and it drifted. And you can see now where the correction factor's different now than what it was, because basically the output potentiometer had drifted up. If you remember from the video, it was like 720 something. I don't remember what it was exactly, but as that swings around, your correction factor is going to change to bring this ADC back down to exactly where it needs to be. So the next video I'll go over the code, and I'll show you how we set this board up. The Arduino, we set it up to use the internal 1.1 volt reference, so we can get millivolt resolution on that 10-bit ADC and give us such accuracy when measuring these caps. And I'll go over the interrupts that I use for these buttons, for the cal buttons, and the show cal functions. It's pretty slick, nothing to it. But anyway, if you have any questions, be sure to leave me a comment, and if you like it, give it a big thumbs up, please. Thanks.